Kylo Limit Loren talking to you about continuity. Where's the best place to buy a lightsaber? At the Darth Mall.
First thing we're going to talk about is continuity at a point. So a function f is continuous at c when these three conditions are met. So the first condition, f of c, is defined. That means there is a point at x equals c that is on the graph of the function. So at x equals c, we have a point on the graph of the function right there. Here, f of c is not defined because we have a hole in the graph at x equals c. The second condition, the limit as x approaches c of f of x exists. So that means that from the left and from the right, your function must approach the same y value. So here, from the left and the right, the function approaches a y value of 1 at x equals c. So the limit of f of x exists as x approaches c. Here, as x approaches c, the limit from the left is going to be 2, and the limit from the right is going to be 1. Those are your y values. So because they approach different numbers, your limit as x approaches c of f of x does not exist here. So the limit as x approaches c of f of x must exist for a function to be continuous at a point. And the last condition, the limit as x approaches c of f of x equals f of c. That means the limit that your function approaches from the left and from the right, that limit must have a point at that particular f of c value. Okay, so whatever the x value is, your function must have a point on the graph there. Otherwise, the limit as x approaches c of f of x will not equal f of c. As you see here, if there's a hole and then we have a point up here, the limit as x approaches c of f of x actually equals a y value of 1. Whereas f of c is actually 3. This is the one that is most commonly tested, so make sure you know this one in and out. It's pretty easy. Just know that the limit as x approaches c of f of x, whatever that limit is, has to equal that particular point right there. So continuity on an open interval. A function is continuous on an open interval, ab, when the function is continuous at each point on the interval. And that kind of makes sense. It has to meet these three conditions. So here you can see f of c is defined for any c in between ab. The limit as x approaches c of f of x exists at any c here. And the limit as x approaches c of f of x will equal f of c, no matter where you choose c here. Whereas here, f of c is defined. Yes, it is. Okay, there's a point at x equals c. The limit as x approaches c of f of x exists. So the limit from the left is equal to whatever y value this is. But the limit from the right is equal to this y value. Therefore, the limit does not exist here. So that would automatically cancel out, and then you'd be done. Everywhere continuous function, that's a function that is continuous on the entire real number line. Okay, so all those three conditions are met in every one of these graphs. There's no holes, there's no asymptotes, it's just an everywhere continuous function. Now, a discontinuity occurs when function f is defined on an open interval ab, except possibly at real number c, and f is not continuous at c. So any x value at which a function is not continuous, at that point there is a discontinuity. So here the function is continuous on the open interval ab. Here function f has a non-removable discontinuity at c. That means that there's actually a jump discontinuity here. We'll talk about that in a second. Removable discontinuity is when function f can be made continuous by redefining f of c. So that's just if at one point on the function there's a hole. Okay, if there's a hole, then that's just a removable discontinuity. We can just bring that point right back in here and cause it to be continuous if we wanted to. But a non-removable discontinuity, that's when f cannot be made continuous by redefining f of c. This is sometimes called a jump discontinuity. So here, there's a jump discontinuity because it's a non-removable discontinuity. There's no way that you could just plug in a point here and now it's continuous. There's actually a gap between two parts of the function. You have a non-removable discontinuity anytime there's an asymptote as well. Now let's talk about one-sided limits. So the limit of a function as x approaches some real number c from the right or from the left. That's considered a one-sided limit. So you can see here, as x approaches c from the left side of the graph, left side of the function, your limit as x approaches c from the left is going to equal a y value of 2. Whereas the limit as x approaches c from the right side of the function is going to equal a y value of 1. Now, limit from the right is the limit of a function as x approaches c from the values greater than c. So that would be the right side of the graph where all the x values are greater than c. It's also called a right-handed limit. So the limit as x approaches c from the right side of the graph is equal to a y value of 1, whereas the limit from the left is the limit of the function as x approaches c from values less than c. That's also called a left-handed limit. If you're approaching c from the left side of the graph or x values less than c, then we are approaching a y value of 2. Also note that the limit as x approaches c of f of x does not exist here because it's approaching two different numbers from the left and the right. there is a jump discontinuity. That's a non-removable discontinuity. Now, continuity on a closed interval. So a function f is continuous on a closed interval ab when f is continuous at each point on the open interval ab. And the limit as x approaches a from the right of f of x equals f of a, and the limit as x approaches b from the left of f of x equals f of b. So that just means that you're continuous on the open interval, so everything in between the two endpoints, and then at the two endpoints, the limit as x approaches a from the right actually equals f of a. So you have a point on the graph of the function f of x at x equals a, and you also, as we're approaching b from the left, the limit as x approaches b from the left of f of x equals f of b. You have a point at x equals b on the graph of f of x. And that's what we just said. The function f is continuous from the right at x equals a and continuous from the left at b. Now let's talk about the greatest integer function. That's a type of step function whose output is the greatest integer less than or equal to the input. So that means if you were to put in, let's say, 1.5. Since you put in 1.5, the greatest integer less than or equal to the input would have to be 1. Therefore, you get a y value of 1. If you were to put in anything between 1 and 2, it would give you a y value of 1. But once you put in 2, then you can jump up to 2 because that integer is equal to the input. A piecewise function, that's a function which is defined by multiple subfunctions, each subfunction applying to a certain interval of the main function's domain. So a piecewise function, you have f of x equals, and then there's 2 or 3 or 4 different intervals on which the function equals different types of functions. Theorem 1.10, the existence of limit, says let f be a function and let c and l be real numbers. The limit of f of x as x approaches c is L. If and only if the limit as x approaches c from the left of f of x equals L and the limit as x approaches c from the right of f of x equals L. So what this means is that the two-sided limit exists if the limit from the left and the limit from the right are equal. So the limit as x approaches c without any plus or minus here, that only exists if the limit as x approaches c from the left and the limit as x approaches c from the right equal the same number. So, for example, here, if we are looking at the limit as x approaches -2 from the left, the limit as x approaches -2 from the left is equal to 6. The limit as x approaches -2 from the right equals 6. Therefore, the limit as x approaches -2 equals 6, because the limit from the left and the limit from the right as x approaches -2 equal the same thing. Therefore, your limit as x approaches -2 of f of x equals 6. Now let's look over here. The limit as x approaches 0 from the left equals 4, and the limit as x approaches 0 from the right actually equals 0. Because these two one-sided limits are different, right? The limit from the left and the limit from the right are different. They're not equal. Your limit as x approaches 0 of f of x does not exist.
I find your lack of faith disturbing because it's example time. Doesn't make sense.
Example 1 says use the graph to determine the limit as x approaches c from the left of f of x, the limit as x approaches c from the right of f of x, and the limit as x approaches c of f of x. The limit as x approaches c, which is 1 here. So limit as x approaches 1 from the left side is going to be a y value of 0. Limit as x approaches 1 from the right side is going to be a y value of 0 as well. Therefore, the limit as x approaches 1 of f of x equals 0. Over here, -1. So the limit as x approaches -1 from the left is going to be a y value of 0. The limit as x approaches c from the right side, it's going to be a y value of 1. Therefore, these two y values are not equal, so the limit as x approaches -1 of f of x does not exist.
You try.
So if our c value is 2, the limit as x approaches 2 from the left side of the graph is going to be a y value of 1. And the limit as x approaches 2 from the right side of the graph is going to be a y value of 2, actually. Therefore, because these two limits are not equal to one another, the left-sided limit and the right-sided limit are not equal, the limit as x approaches 2 of f of x does not exist. Over here, we have the limit as x approaches -2 from the left side of the graph is equal to a y value of -8. The limit as x approaches -2 from the right side of f of x also equals a y value of -8. Therefore, the limit as x approaches -2 of f of x equals -8. Now, please keep in mind that just because there's a removable discontinuity doesn't mean that the limit does not exist, okay? Just because it's not continuous at x is equal to -2 doesn't mean the limit does not exist. The limit will exist if it's a removable discontinuity at that x value. If it's a jump discontinuity, as you see over here, then the limit will not exist. Example 2 says find the limit of the following functions if it exists. If it does not exist, explain why. So first, I have the limit as x approaches -1 from the left of the absolute value of x plus 1 over x plus 1. Now remember, you always try to plug it in first, and if I were to plug this in, I'd get -1 plus 1, which is 0, over -1 plus 1, which is 0. So 0 over 0, that's an indeterminate form. I must try to simplify this somehow. You can break up an absolute value function into a piecewise function. If you pick an x value that is greater than or equal to -1, you're just going to use whatever the function is inside of the absolute value function, inside the absolute value signs. You would just use this x plus 1. And what I mean by that is if I were to plug in, let's say, 2, then I would just use this function right here. I would say 2 plus 1 equals 3. And the absolute value signs don't really do anything, so it's just 3. Whereas if I were to plug in a value that is less than -1, so let's say -2. If I were to plug in -2 here, -2 plus 1 gives me -1. But the absolute value signs make it the opposite of that. So I would actually have to use the opposite of whatever x plus 1 is. That's what this means. The opposite of whatever you get when you plug in x plus 1, because that's what the absolute value signs do. And that only occurs when x is less than -1. So I'm doing the limit as x approaches -1 from the left side. And those are x values that are less than -1, right? You're approaching from x values less than -1. Therefore, you're going to use this portion of the piecewise function. So let's plug in this for the numerator. Now you can see that the x plus 1s are just going to cancel out, and I get the limit as x approaches -1 from the left is going to be -1. Here, I have the limit as x approaches -2 from the right. So if I were to plug in -2 here, you then square that and you get 4, and then 4 minus 4 gives you 0, and the square root of 0, you get -2 over 0. For right now, you're going to say the limit does not exist anytime you get 0 in the denominator, but we'll talk about that more later. Here, you always got to try to plug it in first, and you get 0 of 0. That's an indeterminate form, so you got to go back and try to factor and cancel. So here, the denominator is the difference of squares. That factors into x minus 4 times x plus 4. Now, this could be x minus 4, but you have to factor out -1. Then you can see the x minus 4's cancel out. You can then plug in your 4, and you end up getting a limit of -1 over 8.
You try.
Okay, so you make sure that first you always try to plug it in. So we're going to take this 9, substitute it in for each of the x's. When we do that, we get 9 minus 9 over 9 minus 9, which is 0 over 0. So we then have to find another way to simplify. Since we have an absolute value function on top, we're going to have to break that into a piecewise function. Now remember, when you break an absolute value function into a piecewise function, it's the normal function, just x minus 9, anytime x is greater than or equal to 9. So if I plug in a number greater than or equal to 9, so like let's say I plug in 11. If I plug in 11, 11 minus 9 is going to give me 2. So it's just the standard function, and the absolute value sign is just going to give me that same positive 2 out. But if I were to plug in a number less than 9, let's say I plug in 7. 7 minus 9 gives me -2. But then the absolute value sign changes that number. So we have to do the opposite of x minus 9 anytime x is less than 9. So are we approaching 9 from the left or the right? We're approaching it from the right. Those are numbers greater than 9, so we're going to use this particular function. So we substitute that in to this function up here. Now we can see those cancel out, and we just get the limit as x approaches 9 from the right of 1. And anytime you take the limit of a constant, it's just equal to that constant. Over here, I can plug in that 5 to each of these, and I get 5 over 5 minus 5, which is 5 over 0. That means the limit does not exist. And then right here, the limit as x approaches 4 from the left, I plug in 4 for each of these, and I get 2 minus 2 over 4 minus 4, which is 0 over 0. So that's an indeterminate form. I got to go back and try to simplify this somehow. Let's try to rationalize the numerator. So I'm going to multiply the numerator and denominator by the conjugate of the numerator. That would be rad x plus 2. And I multiply by a form of 1, so it doesn't really change the function over here. When I do that, I FOIL the numerator, and then I'm just going to leave the denominator like this for now to see if something cancels out. You see that these cancel out, and I get x minus 4 left in the numerator, which means the x minus 4s are now going to cancel out. And I'm left with the limit as x approaches 4 from the right of 1 over rad x plus 2. I then plug in that 4 for x. Rad 4 is 2, and then 2 plus 2 gives you 4. So I have 1/4 as my limit. Example 3 says find the limit of the following functions if it exists. If it does not exist, explain why. So first, we're finding the limit as x approaches -1 of p of x, where p of x is this piecewise function here. In order to have a limit as x approaches -1 of p of x, the limit as x approaches -1 from the left must equal the limit as x approaches -1 from the right. And we have, as x approaches -1 from the left and from the right, okay, numbers less than -1 and numbers greater than -1. So let's first find the limits as x approaches -1 from the left. And remember, we use 1 for that because those are numbers less than -1. So that would be all of these numbers. I just find the limit as x approaches -1 from the left of 1. Since it's a constant, it's just equal to 1. Down here, the limit as x approaches -1 to the right. It's the right because its x value is greater than -1. So I plug in -1 for this x, simplify, and I end up getting -2. So the limit from the left does not equal the limit from the right. Therefore, the limit does not exist. And you can see that from the graph here, that the limit from the left is 1, while the limit from the right is going to be -2. And since they don't equal, the limit does not exist.
You try.
Okay, so again, you need to find the limits as x approaches 1 from the right of h of x. Now, from the right means we're approaching 1 from x values greater than 1. So x values greater than 1 would be right here, which means we're going to use this particular function. So if we find the limit as x approaches 1 from the right, we just plug in 1 to this particular function and we get -2 plus 4, which is 2. And then you see the limit as x approaches 1 from the right is going to be 2. Yes, that checks out. So now, example 4, we want to discuss the continuity of each function. We have f of x is equal to 1 over x, and that graph looks something like this. Now, in order to discuss the continuity, we need to first ask ourselves, does the function meet the 3 criteria for continuity? Is f of c defined for all x is equal to c? Does the limit as x approaches c of f of x exist for all x is equal to c? And does the limit as x approaches c of f of x equal f of c for all x is equal to c? Well, as you can see from our graph, we really only need to concentrate on one x value. It exists for all x, but at x is equal to 0, something happens, right? We look, is f of 0 defined? No, there appears to be an asymptote here. So f of c is not defined for all x is equal to c. Now, the limit as x approaches c of f of x, does that exist for all x is equal to c? Well, the limit as x approaches 0 from the left looks like it's negative infinity. The limit as x approaches 0 from the right is positive infinity, so therefore that does not exist for all x is equal to c. Because each of these does not exist, this wouldn't make any sense, so that obviously does not exist as well. Because of this, we know there is a discontinuity in this graph somewhere. So let's go ahead and move forward. Are there any x values for which f of x is undefined? So are there any x values that cause the denominator to equal 0? Yes, 0. So x cannot equal 0. Next, we ask ourselves, do any factors in the numerator cancel out with the denominator? No, there's only a 1 in the numerator, so therefore nothing can cancel out. Next, we then move to the type of discontinuity we have. Because nothing cancels out in the numerator and denominator, and x cannot equal 0, and each of these does not exist, we know that there must be an asymptote at x is equal to 0. We can then classify that as non-removable. And in terms of your answer, if this were asked on a test or the AP test and it said discuss the continuity, what you would say is because f of 0 is not defined and the limit as x approaches 0 of f of x does not exist, there is a non-removable discontinuity, an asymptote at x is equal to 0. Let's try another one. So here we have g of x is equal to x squared minus 1 over x minus 1. Now you recognize the numerator is a difference of squares. That means the quantity x minus 1 cancels out with the quantity x minus 1 in the numerator and denominator, and you're just left with x plus 1, where x cannot equal 1 because that would cause our original denominator to equal 0. So what does this look like? It looks something like this, where we have a hole at x is equal to 1. So if you didn't know this offhand, what you would do, you would ask yourself, does the function meet the 3 criteria for continuity? Is g of c defined for all x equals c? Does the limit as x approaches c of g of x exist for all x is equal to c? Does the limit as x approaches c of g of x equal g of c for all x equals c? We can see here from our graph, we only have one x value that we're concerned with. It exists everywhere, except we're not sure what happens at x is equal to 1. So is g of 1 defined? Is there a y value for x is equal to 1 for this function? No, right? There's a hole here. Therefore, g of 1 is not defined for all x equals c. Now, part B wants to know, does the limit as x approaches 1 of g of x exist? Yeah, as x approaches 1 from the left, your function g approaches a y value of 2. As x approaches 1 from the right, your function approaches a y value of 2. Therefore, the limit as x approaches 1 of g of x is equal to 2. So because that one exists, it must exist everywhere else. So the limit as x approaches c of g of x exists for all x equals c. Now, does the limit as x approaches c of g of x equal g of c? Well, because g of c is not defined for all x equals c, you could say that this must then not be true. Because only one of these is true, we know that the function must have a discontinuity somewhere. So let's move forward. Are there any x values that cause g of x to be undefined? Well, we said x cannot equal 1, right? Because that would cause our denominator here to equal 0. We then ask, do any factors in the numerator cancel out with the denominator? Yeah, one factor in the numerator cancels out with the denominator. That would be x minus 1. Now, because of that, we then look, what type of discontinuity will we have? Well, since that factor in the numerator cancels out with the factor in the denominator, we know there's going to be a hole. And where's that hole going to be? At x is equal to 1. And a hole, we know, is a removable discontinuity, which is just a discontinuity where if you were to plug in 1 point, it would make your function continuous. So here, if I were to put a point here, it would make this whole function continuous. Now, in order to discuss this, your final answer then would be because g of 1 is not defined and the limit as x approaches 1 of g of x does exist, there is a removable discontinuity, a hole, at x is equal to 1. Example 6, we're doing the same thing here, except we have a piecewise function. Now, what does this look like? It looks something like this, where we have y equals x squared for all x less than or equal to 1. And then when x is greater than 1, we have the function 2 minus x. So, again, does this function meet the 3 criteria for continuity? Is p of c defined for all x equals c? Is there anywhere where this function is not defined? No, because these two functions meet at the same y value at x is equal to 1, right? If I were to plug in 1 here, I would get a y value of 1. If I were to plug in 1 here, I would get a y value of 1. So they meet at x is equal to 1. Perfect. So p of c would be defined everywhere where x is equal to c. Now, does the limit as x approaches c of p of x exist for all x equals c? Well, yeah, since we have a function that is defined everywhere and these two meet up right here, the limit as x approaches c of p of x would exist for all x equals c. Lastly, we want to know, does the limit as x approaches c of p of x equal p of c for all x is equal to c? And this is really just asking if there's a hole where a point would be like above it or below it. And there is none of that, so you would say, yes, the limit as x approaches c of p of x is equal to p of c for all x equals c. Therefore, since the 3 criteria of continuity are met, you would say, because p of c is defined, the limit as x approaches c of p of x exists, and the limit as x approaches c of p of x equals p of c for all real numbers c. P of x is everywhere continuous. Now, example 7, we again have a piecewise function where it's a parabola for all x is not equal to 1. But at x is equal to 1, we have a point at 1, 5. So let's discuss the continuity. First, is g of c defined for all x is equal to c? Yes, at every x value, we have a corresponding y value. Does the limit as x approaches c of g of x exist for all x equals c? Yes, even at this little hole right here, the limit as x approaches 1 from the left is equal to 3. The limit as x approaches 1 from the right is equal to 3. Therefore, the limit does exist. Now, the last criteria for continuity asks, does the limit as x approaches c of g of x exist and equal g of c for all x equals c? Well, you can see that the limit as x approaches 1 from the left and the right is equal to 3. But the y value that goes with x equals 1 is 5. So these two things are actually not equal to each other at x is equal to 1. Because of that, we know there's going to be a discontinuity somewhere on the graph. So we continue. Are there any x values for which g of x is undefined? Well, we said g of c is defined for all x equals c, so no. We know g of x is defined for all real numbers. Do any factors in the numerator cancel out with factors in the denominator? Well, there's not even a rational function here, so no. What type of discontinuity do we have then? Well, since we know g of x is defined for all real numbers, and there's no factors in the numerator that cancel out with factors in the denominator, we just know that the limit as x approaches 1 of g of x does not equal g of 1. There must be a hole at x is equal to 1. Now, is this removable or non-removable? Well, we know a removable discontinuity is just one where if you were to plug in a hole, it would make the function continuous. So yeah, if I were to plug in a hole here, we would have a continuous function. So this is removable. Now, all you say to discuss the continuity would be, because the limit as x approaches 1 of g of x does not equal g of 1, there is a removable discontinuity, a hole, at x is equal to 1.
You try!
So again, we're discussing the continuity. This time it's of h of x is equal to sine of x, which looks something like this. And we look at the 3 criteria for continuity. Is h of c defined for all x equals c? Yes, there's no holes or asymptotes for sine of x, so yes it is. Does the limit as x approaches c of h of x exist for all x is equal to c? Yes, again, there's no holes or asymptotes here, so it does exist. And does the limit as x approaches c of h of x equal h of c for all x is equal to c? Yeah, there's no holes where there's a point above it or below it. So you would say, yes, it does. Because all three criteria of continuity are met, you would say, because h of c is defined, the limit as x approaches c of h of x exists, and the limit as x approaches c of h of x equals h of c for all real numbers c, h of x is everywhere continuous.